Hi, how are you? So we're going to look at Lewis structures. Yeah, okay. So we're going to look at how to draw and determine the shape of a molecule, all right? Lewis structures are for molecules. We will draw the discrete molecule itself, right? And from that, we can determine the shape of the molecule, the polarity of the molecule, and some physical properties of the molecule. Yeah, I'm thinking too much. Okay, so let's see here. We're going to draw Lewis structures for molecules. There's a lot to this, meaning you don't just say, oh, I got it. You know, it's going to expand through the next few lessons. Some of you guys don't want to hang in there with me. So you got to hang in there with me, okay? Let's see. We are going to count valence electrons. Right, let's abbreviate that. Negative S electrons available for bonding. Available. Boy, it's available for bonding. You guys took your 1.5 through 1.8 quiz today. I've been grading all those papers today and haven't stopped all day. It's about 5 o'clock now, I think, or a little bit later. Okay, we're going to count the valence electrons available for bonding. That was a little random, wasn't it? Okay, so let's keep this really simple. Like, I know what the structure is going to look like when I'm finished, okay? Actually, let's keep going. Count valence electrons available for bonding. Determine central atom. Now, well, never mind. Determine central atom. Arrange atoms. Central atom. Hydrogen. Never. Central atom. Okay. Typically, the central atom is the least electronegative atom. Typically. And it's also usually the first atom that's written in the compound. The formula for the compound, like ClO4, chlorine's going to be the center. PO4, P is going to be in the center. SO4, S is going to be in the center, etc. NH4, N is going to be in the center. Now, you need to realize that carbons love to be in the center, right? Carbons, there's a whole class in chemistry called organic chemistry. It's all about carbon. All about carbon. Carbon this, carbon that. I mean, there's so much to learn about carbon compounds. There's a whole class on it, and it's hard. So carbons love to form long chains, or gosh, what would I call it? Or cyclical compounds. Or I'm going to write cyclical compounds. They call them cyclo compounds, cyclical compounds. So you just need to know that if you see like C, 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 etc., or, you know, let me go up. Whoa. Or like C, 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 C. That would be like a cyclical compound. So you just need to be aware of that. If you ever see carbons, they're all going to be lined up or chained. The chain may bend in some way, right? But carbon loves to form bonds with itself. It's got those 4 valence electrons, 4 empty, or the 3 half-filled orbitals. It just works really well. So just be aware of that. Hydrogen is never going to be in the center. That's very important. Don't put hydrogen in the center. I'm going to say, you didn't watch my video, did you? Or anyone's video for that matter. Okay, so I'm going to count my valence electrons. I'm going to determine the central atom. I'm going to arrange the atoms. We're going to call those terminal atoms, right? And that means they are not the central atom. So they're the atoms on the outer edges, okay? I'm then going to be monotonous until I start memorizing things. I'm going to connect central atom with terminal atoms. And I'm going to do that using bonding pairs. Okay, well, pair means two. Pairs of what? Of electrons. Hopefully you knew that. We're showing how electrons are being shared in these molecules, right? Covalent compounds are called molecules. How are they shared? And we'll do that with a line, right? And you don't draw it, but that line, you know, it's kind of like there. There's a line that connects those two electrons, and this is your covalent bond, right? So we're showing that where those bonds are and where they're arranged around the atom. That is a single bond. There are double bonds. Okay. And there are triple bonds. Okay. And this one is shorter. We've already talked about this, and thus stronger. And you can go ahead and identify it yourself that this is longer and weaker. Now, guys, I'm going to go ahead and take my first tangent here. Okay. A single bond. Let's see, I don't have room for it. The single bond is composed of, this is this is basic memorization. It's the overlap of orbitals. It's composed of one sigma bond. Okay? And that sigma looks like that. All right? The double bond, it's just memorization. If you get into organic chemistry, you can understand what it means. For now, you don't need to. It's composed of one sigma. They may have even gotten this out of the curriculum, I'm not sure. Right? And one pi bond. Oh, that's a sigma and that's a pi. I messed up. I probably shouldn't have taken this tangent. I apologize, y'all, but I don't want to restart this video. Sigma is like that. Sigma is like that. And pi is like that. Duh, right? And then this is composed of one sigma, right? Which is kind of like that, and two pi. Those are overlapping S and P orbitals and stuff like that. Okay, let's get back on track, Ms. Murphy. Count the valence electrons available for bonding. Determine the central atom. Arrange the terminal atoms. Connect the central atom with the terminal atom using bonding pairs. Okay, then our goal from that point on will be to satisfy octet for all atoms by placing all electrons and forming multiple bonds. That means double or triple if necessary. Okay, it takes practice, but it gets pretty easy. Just take the same steps all the time, all right? Now, there are always exceptions. For example, here. So first of all, someone might be thinking, what does she mean by octet? Well, what Ms. Murphy means is that most all elements should be surrounded by 8 electrons. Octet means 8, okay? However, there are some exceptions to that. H only gets max of 2 electrons. He's too small. He only has that one first energy level to hold electrons. So we can't start piling. We can't put it. So he's never in the center, right? You'll get one line to him. That's it. He's always on the outside. Okay. There are sub-octets. And that's where central atom has central atom has less than 8 electrons. And that's typically, guys, your BeX2. This is often a halogen. And your BH3. You will see that you have sub-octets there, okay? And to be honest with you, I can't think of another one. But recognize that those guys, you don't need to be forming multiple bonds. They can't handle the multiple bonds. They're too small for that as well. Okay, and then you can also have expanded octets around the central atom, and that's obviously going to be more than 8, right? More than 8. Sorry about being messy. More than 8 electrons around the central atom. I'll try to start writing more neatly. And this can happen as long as, right? So not everybody can have an expanded octet. You must have d orbitals. Oops, I went to write 3, but I don't need to write 3. Must have d orbitals in order to have a expanded octet, right? In order to have an expanded octet. You can't have an expanded octet without the presence of the d orbitals. And the d orbitals, remember, that's the first time you see the d orbitals right there. So that means period 3 and below elements can have an expanded octet, but the ones in 2 or above cannot. So nitrogen cannot, but phosphorus can. Okay. And that's about it for now. If you ever have sometimes you have odd number. And what you'll see is you will have a free radical. That's what they call that. You'll end up with 1 electron. Right, think about it. If it's not an even number and it's odd number, you divide by 2, you're going to have that remainder of 1. You will end up with 1 stray loner electron. It's called a free radical. I often see it on nitrogen, 5. And it will sit on that central atom. Like that right there, okay? And then you would see, you know, other things coming off, but that is your free radical right there. And it is not stable. Like you're not gonna see that last around. It's gonna form a single bond with somebody, another guy around him. We would call that dimerizing. If there was, I'm just gonna go ahead and finish it for you rock stars out there, right? Imagine there was one of each. Well, let's say this was NH3. This was NH3. Well, if you do the math, 2, 4, 6, 7. Oh, it would have to be NH2. Sorry. 5, 6, 7. Yeah. Anyway, I think I've gone too far. Let me just keep it like this. N lone free radical, N free radical. Whatever else is going on over here, don't you think those guys are going to come together? We'll call that dimerize. These are just things I say because I've seen them pop up. You know, it's not like the heart of a question, but kids will be like, what does that mean, Ms. Murphy? And I'm like, oh, well, let me tell you. So since I'm here on video, I feel like I can talk longer than normal. I apologize. Okay, let's get to some examples. I'll try to hit on several examples. Most of these are very easy, but as soon as you start assuming you will make a mistake. All right. Start with pH3. All right, count up our electrons. He's got 5 valence electrons. And we've got 3 hydrogens. Each has 1 valence electron. That gives us a total of 8 valence electrons available for bonding. I must use all 8. Nothing more, nothing less. Stick to the rules. Let's see who's going to be in the center. Hydrogen, wherever it is, phosphorus will be. I'm going to put hydrogen here, and hydrogen here. I'm going to spread them out. Well, I know where I'm going. So that's what I'm going to do. And then I'm going to connect them using electron pairs. Out of my 8 electrons available for bonding, 2 have been placed there. I have 6 more. 2 will be placed there. I have 4 more. 2 will be placed there. I have 2 more. Now, listen to me, because I didn't put this in the rules. Too much writing. So, I've got 2 more electrons. Let's look at our central atom. Let's count the electrons around him. He's got 2, 4, 6. Well, the goal is to have 8. There happens to be 2 left over, right? Those 2 right here. So let's put them right there. They're not bonded. So they are lone pairs. So 3 bonding pairs, 1 lone pair. And I would also say that I have a total of 4 domains. So I think you could infer what a domain is. It would be this domain, this domain, this domain, and this domain. All right? Okay, that's cool. Now, how do I make sure that that's right? Well, let's check it. Always check it. Hydrogen, what I see, let me erase some of these lines here. Oh man, why don't it get the whole thing for me? Whole. All right. Yeah, that's what we need. Oops, okay. Easy enough to draw back. Okay, so we just need to check it. So hydrogen always gets a total of 2. Well, right here, I see that hydrogen has his 2, right? 2 electrons for hydrogen. If you know where we're going, right, then you know what you should do. So hydrogen's happy. Now I've got this hydrogen. That's 2 electrons for hydrogen. I should be simplifying that for this hydrogen. So what that tells me is this hydrogen is happy. He's satisfied. This hydrogen also has 2 electrons. Hydrogen's happy. Now let's look at phosphorus here. Well, phosphorus has 2. They're sharing these. 4, 6, 8. Beautiful. We have 3 bonding pairs and 1 non-bonding pair. We've used up all of our electrons. Everybody's happy. That's what we should look like. Okay. HCl. Count up your electrons. 1. Count up your electrons. 7 equals 8. HCl. No one can go in the center because we only have 2 elements. So to ask who is in the center doesn't really make sense. Connect. 2. Well, we had 8. We just used 2. There are 6 more. That is a 6. There are 6 more electrons we need to place. Well, hydrogen's happy with his 2, right? Because what you need to realize is these electrons really belong to hydrogen. Those electrons also belong to the chlorine, not chloride, because it's not an ion, and they're sharing them. They both lay claim to those 2 electrons. So right now, hydrogen has 2, and that's perfect. Hydrogen always gets 2. That's it. Nothing more, nothing 2. So that means I need to place my focus on making sure chlorine is satisfied, and I can do that by using my 6 remaining electrons. 2, 4, 6. He's now got 2, 4, 6, 8. He's got 2. Everybody's happy. And that is what this should look like. Now, make sure that you draw your lone pairs or you will lose points. Let's draw another one. Let's look at Nh4 Plus. These are all real simple. You will be faced with some that are more challenging, but not too many really. 5 plus 4, right? That 4 is because I have 4 hydrogens. Each donates 1 valence electron for a total of 4 valence electrons. And then this plus charge, how do I become positively charged? Well, I lost an electron. So 5 plus 4 is 9 minus 1 equals 8 electrons available for bonding. All right, so let's place our elements. Hydrogen never goes in the center. 2, 4, 6, 8. Oh, we're out of electrons, so I can't add anything else. Let's see, hydrogen here is happy because he's got his 2. All hydrogens are happy because each hydrogen has his 2. And then we see that nitrogen's happy because he's got the 2. He's got the nitrogen 2, 4, 6, 8. So hydrogens have 2, nitrogen has 8. We're going to see this tetrahedral shape. Now, because we have this charge right here, we need to put him in brackets. We need to put that charge right there. Otherwise, it will be wrong. Okay. Okay. Let's do something like CO2. All right. 4 plus 2 oxygens, each donates 6. That's 12 plus 4 equals 16. Let's put carbon in the middle. We already said carbon loves to be in the center. Let's put oxygen as far apart as we can. Let's connect the dots. 2, 4. All right, we have 16. There are 12 left over. Always take this approach. I'm going to fix my outer edges first. 2, 4, 6, 8, 10, 12. Sorry, I was just thinking about my numbers. Okay, so what I'm going to do is I just did 16 minus 4 is 12. I'm out of electrons. Sorry, I just kind of farted for a minute. I'm out of electrons. Okay. So now what I need to do is I can't stop there. I need to look and see that everybody's satisfied, because if they're not, I need to start moving things around. And in fact, that's what I'm going to have to do. So I can look at oxygen here, and I see that he's got these 2, these 2, these 2, and then these 2. So oxygen has 8. Cool. Let's erase oxygen's 8 that we identified so that they don't confuse us with carbon. Carbon here only has 4, right? He's got these 2 and these 2. That's not good, right? Carbon is not an exception. Carbon needs 8. Let's go ahead and look at this oxygen. Oxygen here has 2, 4, 6, and those 2, which is 8. So it looks like everybody on the outside is happy, but carbon is not. So what we're going to do is we're going to form multiple bonds. We're going to have this carbon over here on the right-hand side, right? On the right-hand side. I'm going to not let him keep those electrons. Remember, there was a pair over there. But I'm going to make him share those electrons right here, so that now they belong to both him and carbon. And now I see that carbon has a total of 2, 4, 6 electrons. So I'm going to do the same thing, and I'm going to make this oxygen share. And I'm going to place, oops, goodness gracious. I'm going to place those electrons here. Okay, instead of oxygen keeping them by himself, he's going to share them with carbon. And now what I see is carbon has 2, 4, 6, 8. And I see that everyone is satisfied with me having rearranged this. Okay, and I used all my electrons, nothing more, nothing less. Now, you maybe think of, well, why did she do it that way? She could have done it a different way. and you're right, and we'll learn about that later. Okay, that's where something called formal charges comes in. I don't want to do too many because I want you to have to do some, but let's do something like this, C3H8, just because it's so easy and students get confused. Guys, I'm going to line my carbons up in the center. Oops, step 1, 4 times 3 equals 12, plus 1 for hydrogen times 8 hydrogens equals 8. That's 20, okay? So I'm going to go 2, 4. Got to connect them. The hydrogens, guys, are going to be all around here. 1, 2, 3, 4, 5, 6, 7, 8. Check this out. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I'm out of electrons. Each carbon is satisfied. If you look, 2, 4, 6, 8, 2, 4, 6. Let me get a different color. 2, 4, 6, 8. And then our last color, 2, 4, 6, 8. Okay. And then if you notice, each hydrogen only has its 2. They're usually pretty simple. If this is N and this is 2N plus 2, then these will all be single bonds. Something I learned. Let's see if we were to do C3H6. I hope I don't mess up, because sometimes you make these up and they're not right. 4 times 3 equals 12 plus 6 equals 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. Yeah, that's not going to last. Okay, I'm going to stop. I'm going on a tangent, but I need to remember. You don't need to know, but I do know. I just can't remember what those little equations are, but I don't feel like coming up with it right now. Sorry, I apologize. So that's about it. You know, make sure you realize that if there is a negative charge, okay, we would add up our 5 valence electrons there. We would have our 3 oxygens times their 6 valence. And because of the negative charge, we would add 1. If it was a 2 negative, we would add 2, right? Well, 3 times 16 is 18 plus 6, that would be 24, okay? So let's put our little nitrogen in the center. You know, maybe you pause it and fast forward it and you see if you get the right answer. So stop here and then come back for the right answer. Nitrogen, oxygen, 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 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay. So I'm out of electrons. My nitrogen, right, oxygen has 8, 8, 8. However, my nitrogen over there only has 6, and that is no good. Nitrogen wants his 8 too. So what that means is that one of these oxygens is going to have to share with him. So instead of these two staying here, I'm going to get rid of them, and I'm going to share them right here. Okay, so now nitrogen has 2, 4, 6, 8. Good, right? And notice everyone does. Oxygen, 2, 4, 6, 8. Nitrogen, 2, 4, 6, 8. Oxygen, 2, 4, 6, 8. Okay, now what we haven't discussed is how these bonds should be arranged in terms of ankles. We'll keep that. And we will now recall that this is, oh yeah, and then our last oxygen down here also, Mr. Murphy's a nut, 2, 4, 6, 8. Okay. And recall that this guy has a charge. So what do we need to do or it's wrong? Put brackets around it and put the charge out there. Okay. So you've got to do all of those things except for color everything, but it looks pretty all right. And that's about it. Let's do one more. Okay, guys. CH3OH. Okay. 4 plus 3 times 1 plus 6 plus 1, 7, 10, 14. C, H, H, H. All right, I just did that fast. That's what that means, guys. CH3 looks like this. It's referred to as a methanol group, a methyl group, okay? You don't need to know that. It's just nice to know things sometimes. O, H. Now let's count some electrons, okay? We just connected them. We know they have to be connected. So let's count them. 2, 4, 6, 8, 10. Okay, we used 10. We had 14. Okay, so about 4 left over. Well, look, everybody's happy. It's like that oxygen right there. Doesn't he need some more? Okay. Anyone from last year thinking how Miss Murphy used to stress that whenever there was a bonding and 2 non-bonding, like water, and it would be bent? You're right. And this would be bent. And because of that, it would be more polar. So I'm going to get there. I'm just going to save that for another day because it's actually one of the topics is using that theory. Okay. So I'm not getting into that yet. Okay. But if you're thinking that, good on you. Yeah. All right, guys. So I'm gonna leave it at that. I don't want to do too many. There are, however, triple bonds, right? Let's go ahead and look at nitrogen. And just remember, guys, just memorize, nitrogen often forms triple bonds. And oxygen often forms double bonds. That's just worth knowing. Your halogens, fluorine, chlorine, bromine, iodine, hydrogen, these are single bonds only. They do not form multiple bonds, okay? Your oxygens tend to form double bonds. O2, double, and then N2 is triple, all right? So we will end with the N2, which is a fun one, okay? But these are single bonds only. Oxygen is a double bond often, O2 always. N2, N often forms, he does triple, double, single, but N2 is always triple. So in 2, we've got 5 times 2 equals 10 electrons. In 2, 4, 6, 8, 10. And you see that this nitrogen on the side, oh my gosh, how do I get those papers, that thing out of my way? Oh, right, he's got 2, 4, 6, 8. However, the other guy only has 2, 4. So this guy over here needs to share it with him. We need to get rid of those. Actually, let's keep those. Let's get rid of those and put them here. And let's get rid of those. And let's share those as well. So now you can see that each one has 2, 4, 6, 8, 2, 4, 6, 8. And we have N2. So very strong bonds, very short, very strong, okay? Lightning is one of the only natural things. Lightning and nitrogen fixing bacteria can break this bond, right? So it's pretty cool that it's one of the strongest bonds out there, and bacteria can break it, as can lightning. So that bacteria is pretty cool, right? And you AP Bio kids should know what I'm talking about. I'm going to leave it at that, okay? thank you for hanging in there with me. It's worth it because that's where I get the little things I forget. So see you later. Bye.